when I'm saying this can be faster, how much faster can this be? So we've done for you the cleanest possible and the most honest benchmarks. And this is so honest, I'm showing you a slide where I'm actually not faster. So here's the thing. The whole thing about abstract machines is that they go faster on the bookkeeping side of things. But if you have no bookkeeping, if your hardware representation has been made so as to do a special kind of computation really fast, it turns out that saving on the bookkeeping doesn't save anything at all. So Fibonacci is the example of that. What that means is Fibonacci is putting stuff on your stack, adding them, putting more stuff on the stack, adding them, and so on and so forth. And that kind of permutation is already quite optimized. RISC-V will produce code that does that really fast with minimal amount of blah blah around the additions. And so it's really difficult to build SP1. So that you can interpret all of this, there's a blog post, you can read the blog post, have all of the detail, you can have all the code, you can reproduce all of this. I'm just giving you a very quick flavor. Sphinx is our slightly tuned variant of SP1. That is a fork that has minor differences. You have SP1 on the right. Lurk literally shares code with Sphinx. So we call into it as a library. We do not actually care about RISC-V at all. So of course we do not use a RISC-V prover, whether it's Sphinx or SP1, but there are some interesting functions and some interesting cryptography in there, including a fancy lookup argument. This is the cleanest differential benchmark you'll see ever. We're literally just implementing the thin abstract machine layer on top of a native prover and sharing everything in the prover, the good and the bad. We also have numbers for RISC-0 and Jolt. If you're interested, go see the blog post. So the pure Fibonacci of 50,000, of 10,000, not exactly faster, but when you're doing something, very esoteric, such as I'm going to take the vector of elements from 0 to 1,000, and I'm doing the Gauss summation, like I'm doing 0 plus 1 plus 2 plus 3 until 1,000. Turns out we're a little bit faster because there's a bit more bookkeeping involved. And when I say a bit faster, I mean a real bit faster. When you look at Fibonacci, there's one thing that has always frustrated us, which is that Fibonacci itself is computed in a messy way that doesn't actually even take advantage of the SIMD capabilities of the existing processors, if you think about it. So we thought, hey, or at least a genius among us, I'm actually not responsible for any of this personally, thought, hey, you know what? You can actually make Fibonacci go fast. And we have a fast Fibonacci implemented a matrix multiplication. 2x2 matrix multiplication, which will really actually make the stuff work. And there, well, there's a little bit of bookkeeping too, showing that RISC-V interpreted need to figure out how to access the elements of that matrix. And in that bookkeeping, that now stuff works a little bit faster. So that's pretty cool.